Okay guys, in this video we are going to discuss two experiments that led to the development of modern physics. One of these involves blackbody radiation. Blackbody radiation is emitted whenever you have a material object at a finite temperature. Okay? So any material object emits electromagnetic radiation when it has some finite temperature. You've observed blackbody radiation. For example, if you've ever looked inside a toaster oven and when the toaster is running and you see that the metal wires are glowing kind of orangish red, that is blackbody radiation that you can see. It's in the visible range of the electromagnetic spectrum. Objects that are at kind of room temperature, including our own bodies, they're emitting electromagnetic radiation as well. It's just that it's in the infrared region of the electromagnetic spectrum. The term blackbody refers to a hypothetical object that is a perfect absorber and emitter of light at all electromagnetic frequencies. Real objects, they don't emit all frequencies of light equally well. They have some bias towards certain frequencies and other frequencies, but a blackbody is a perfect absorber of all electromagnetic radiation. The idea behind blackbody radiation, or our understanding of blackbody radiation, is that there are atoms within the material that are oscillating back and forth, okay? And the atoms, the object itself is in equilibrium with some thermal bath. So there's a thermal distribution of vibrations happening within the material object involving these atoms somehow. And what the blackbody spectrum is, the electromagnetic radiation that you observe for this object at a finite temperature is related to the distribution of energy within the object, the atomic level distribution of energy within the object. And so atoms that are sort of oscillating back and forth with a particular frequency can absorb and emit light with that same frequency. And at different temperatures, we find that the blackbody spectrum of an object is different. So as you change the temperature of the object, the distribution of vibrations changes. And we're going to take a look at some figures on the next slide here. So what you're seeing here, so this is the blackbody intensity, so the intensity of the blackbody radiation as a function of wavelength. Okay, so this is different wavelengths of light that you would observe. And then the different curves here this dark orange curve, the yellow curve, the green curve, and the blue curve, these correspond to an object at different temperatures. So at cooler temperatures, the blackbody spectrum is it peaks well in the infrared range of the spectrum. And as you go to higher and higher temperatures, you see that the peak of the blackbody spectrum, that is the point where the spectrum is most intense, shifts. And as you go to higher temperature, it shifts to shorter and shorter wavelengths of light. Classical physics is incapable of describing these blackbody spectra. In fact, classical physics predicts that the curves don't turn over. See how it turns over here? It peaks and then turns over as you go towards the ultraviolet range. Classical physics predicts that the spectrum just keeps going up and up and up and up, which is not what is observed and would be unphysical if it did keep going up like that. This is called the UV catastrophe. It refers to the failure of classical physics, which is based on continuous energies. It's based on the fact that, or it's called the UV catastrophe because classical physics fails to predict the blackbody spectrum in the ultraviolet range of the electromagnetic spectrum. So there's something wrong with classical physics, and what I'm hinting at here is that it has something to do with the assumption, the classical assumption, that energy is a continuous quantity. And around 1900, Max Planck, a German physicist, he was thinking about blackbody radiation, and he made the proposition that perhaps the atom's energy, that is the energy of these atomic oscillators, perhaps they are not continuous, but rather they are discrete. That is, the energies are somehow quantized. And so he proposed a model for how the energy of the atomic oscillators are related to the frequency of oscillation. He proposed that they are an integer multiple of the frequencies, and then h is a proportionality factor that he introduced that converts you from units of frequency to units of energy. And so these numbers n here, these integers, these are called, this is called the quantum number. Okay? You see what the effect of the energy of the quantum number is that it restricts the allowed energy levels of the vibrating atoms. Okay? Using this model, Planck successfully predicted the experimentally observed blackbody spectrum. He was able to fit his model to the data and find the proportionality factor h, which we now call the Planck Constant. This is a fundamental constant of the universe. It has the value of 6.626 times 10 to the minus 34 joule seconds. You can see that energy should be measured in joules. Hertz is measured in reciprocal seconds, and so the units of Planck's constant should be energy times seconds. So what we find, what Planck's model does is it shows that there is evidence that microscopic particles have quantized energies, even though it appears that macroscopic objects do not. Another important experiment that came around, or that was explained around the turn of the century, this time by Einstein, is called the photoelectric effect. So the photoelectric effect refers to the observations that electrons are ejected from a metal surface whenever you irradiate that surface with ultraviolet or visible light. These are the observations of the experiment. The light must have some minimum threshold frequency in order to observe the photoelectric effect. And that's illustrated here in the figure. Here we have a red photon, or I shouldn't say photon yet, I should say light corresponding to, light with a wavelength corresponding to red light. Here we have, there is the frequency of the light is insufficiently large to observe the photoelectric effect. However, if you go to a shorter wavelength, which has a larger frequency, you will observe electrons being kicked out of the metal. And if you go to even shorter wavelengths with even higher frequencies, you'll find that the photoelectrons are emitted with a higher kinetic energy. That is, the kinetic energy of the electrons is linearly increasing with the frequency. So once the photoelectric effect is observed, the higher the frequency of the light, the faster the electrons are moving. It turns out that the electron kinetic energy is independent of the intensity of the light that you use. So it doesn't matter how bright the light is. For example, you could use the brightest red light in the world, and you would still not see the photoelectric effect. Likewise, you could use the faintest violet light, and you would still see a photoelectric effect. The only thing is for a very faint light, you would have a very small number of electrons being emitted. So the photocurrent, the number of electrons that emanate per second, is proportional to the brightness of the light. Classical physics is unable to explain these different observations because according to classical physics, the energy of the light wave should be proportional to the brightness of the light. But it turns out that that is not the case. Around 1905, Einstein proposed that the light must somehow be quantized, and he used this to explain the photoelectric effect. Eventually, the term photon was coined, which refers to a quantum, a little bundle, a little particle of light that contains the energy of the light. And so here is the relationship that he came up with for describing the energy of a photon. He says that the energy of the photon is proportional to the frequency of the light, not the intensity of the light. And the proportionality factor is Planck's constant. Here in this second relationship, what I've done is I've used the relationship between the speed of light, the wavelength, and the frequency to write the energy of the photon in terms of the wavelength. Okay, so both of these equations are important. We're going to do some calculations on them in a second. But back to the photoelectric effect first. The idea here is that photons, little particles of light, strike the metal and transfer their energy to the electrons within the metal. Okay? Einstein used a conservation of energy argument to explain the observations in the photoelectric effect. So for example, the energy of the photon is equal to h times nu, and then that energy of the photon is divided into two parts. The first part is the energy required to simply pull the electron out of the metal. Okay, so this nu naught here, this is the threshold frequency for pulling a photon off of a metal surface. Then the remainder of the photon's energy then goes into exciting the electron's motion. And so this is the kinetic energy of the electron. 1/2 mass, this is the velocity of the electron squared. It's confusing because the symbol for frequency and the symbol for velocity look very similar, but they are different. Okay? So the photon's energy is divided into two parts. One part pulls the electron off the metal. The other part refers to the kinetic energy of the electron after it absorbs this photon. And what you find here is that the kinetic energy of the photon then is linearly dependent upon the frequency of the light, which is exactly what's observed. This idea that light, it's known that light has wave-like characteristics, right? Light undergoes interference effects, it diffracts, it has a wavelength and a frequency, etc. Light definitely has wave-like characteristics. But in this photoelectric effect, the light is exhibiting particle-like behavior in the sense that a little portion of the light hits something and transfers its energy. That's something that particles do. And so this is referred to as the particle-wave duality of light. The fact that light exhibits characteristics of both particles and waves depending on what experiment you're doing. Well, here's some conceptual questions. Well, no, these are actually quantitative problems that we need to be able to solve. We need to be able to calculate the energy of a photon. And so here we're talking about red light coming from excited lithium. Here we've got a wavelength of 671 nanometers, and we're being asked to calculate the energy of a photon of red light. And then the follow-up question, calculate the energy of a mole of these photons. So here's the photon energy formula. E equals h times the frequency, and then you can substitute in for the frequency, you can substitute in the speed of light divided by lambda. So this is coming from the relationship that we worked with in the last video. You substitute that in here to give you this one. So let's calculate the energy. We'll plug in Planck's constant, 6.626 times 10 to the minus 34 joule seconds. We'll take that times the speed of light. And then we're going to divide by that wavelength, 671 times 10 to the minus 9 meters. And we'll run that through our calculator. That gives us 2.96 times 10 to the minus 19. This is going to be units of joules. Right? You see the seconds cancel, the meters cancel. The energy of the photon is expressed in joules, and one photon has a very small energy. What about a mole of photons? What we'll do is we'll multiply that by Avogadro's number, 6.022 times 10 to the 23 photons per mole of photons. And we're going to get a much larger number. Here I'm getting 178 kilojoules per mole. Okay, and that's macroscopically observable. That's comparable to the energy changes that you would observe in a chemical reaction. Okay, so that's a significant amount of energy when you think about a mole of photons. Part B, you are given an assortment of wavelengths, and you're being asked to calculate the energy of each of these photons. I'm just going to leave that as an exercise for you. You just need to substitute it in these different values for the wavelength. I will work part C. Part C gives you a frequency. It's talking about microwave radiation, the same microwaves that are used in microwave ovens. Typical microwave frequencies, 3 times 10 to the 9th hertz. Calculate the energy of one photon. So here we just need this portion of the expression, plug in Planck's constant, times this frequency, and that's going to give us the energy. And so we're getting 1.9, we'll make that, we'll just round it up to 2.00, times 10 to the minus 24. No, I made an error here. Oh no, that's the correct frequency. So I got 2 times 10 to the minus 24. That would be units of joules. So you want to be able to calculate the energy of a photon from both the wavelength and the frequency of light. Here we have some conceptual questions related to the photoelectric effect. Essentially, we want to evaluate these as true or false statements and then try to correct the statement if it's false. So statement A, increasing the brightness of light increases the kinetic energy of the ejected electrons. That is false. That's what classical physics would predict, but that's not what's observed. What is observed is that the kinetic energy of the photoelectrons increases when the frequency of light increases. So to make this statement correct, you would replace the word brightness with frequency. Increasing the light wavelength increases the kinetic energy of the ejected photoelectrons. That's actually false because the wavelength of light is inversely proportional to the frequency. So in order, and it's the increasing frequency of light that increases the kinetic energy of the electrons. So you should actually decrease the light wavelength in order to increase the kinetic energy of the wavelength, in order to increase the kinetic energy of the electrons. So to correct the statement, you should make that word decreases. Increasing the light brightness increases the number of ejected electrons. That statement is true. We don't need to change it. Increasing the light frequency increases the number of ejected electrons. That statement's false, and we need to rewrite statement D as statement C. It should say brightness, not frequency. Okay, so with that, I'm going to go ahead and stop this video, and we're going to talk about the Moore model in the next one.